All right, are you ready to talk reaction rates? Let's get started. First of all, you should remember collision theory. Remember, reactions only occur when there are effective collisions. What is effective collision? What is an effective collision? What does that mean? Well, do you remember? Two things. One, enough energy. So it has to be greater than or equal to the activation energy. And there has to be the right orientation. So they have to line up right? Line up right and have enough energy. Two things. What is the rate of a reaction? Well, it's the speed at which a chemical reaction occurs. And we call that in chemistry kinetics. Kinetics at this unit is the study of reaction rates. So how do we measure rate? Well, we can look at how much product is formed, or we can look at how much reactant is being used. It's kind of going to be the same, but that's two ways. We could either look at the end or look at what we're using up, okay? So here's a graphic, all right? So let's get a color here that's different. So here you can see we started, this is the amount of reactant we started with. This is the amount of product we started with. Over time, the amount of product is increasing, and over time, the amount of reactant is decreasing. So as this reaction progresses, there's less and less reactant and more product. Here's another example. So we start out with 1 mole fitting in this container. We have all reactant. As the reaction progresses, we end up with more of the product and more of the product. So the amount of product is increasing and the amount of reactant is decreasing as the reaction continues. Not all reactions occur at the same rate. So let's look at a visual. So here you can see these reactions are all occurring at the same time being poured. Now watch. Wait, what? They are not occurring at the same rate, so something must be different, okay? For example, it's like on the stove, if we're both cooking eggs and I turn my burner up higher, my eggs are going to cook faster. So what was different here? Well, we're going to talk about some of the things that we can do to change rate. So rates can be shown graphically. A steeper slope, it's occurring faster. A flattened slope, it's occurring slower. We can also show concentration in a graphic format, but when we're talking about rate, we're really looking at what we were in the previous slide. So the number of effective collisions determines the rate. So remember, we got to collide with enough energy and in the right orientation. So any factor that changes the number of effective collisions can change rate. So remember, lining up correctly, the correct orientation with enough energy. So what factors can we change to change the number of effective collisions or change the rate? Well, let's see. Here's one. Concentration. What does that mean? The amount of substance. So look here. See in this beaker right here? See how there's very few particles, and then as we go this way, more particles, more particles. So we are increasing the concentration. When we increase the concentration, there's going to be more collisions. Okay, it's like being on a crowded bus. You're more likely to bump into somebody. And if there are more collisions, some of them are bound to be effective. So the number of effective collisions is going to go up. That's going to increase the rate. On the other hand, if we decrease the concentration, we're going to have less collisions, which is going to decrease the rate. So if we want to increase the rate of the reaction, we have to increase the concentration. We have to put more particles in the same space. Okay, so again, as we increase the concentration, there are going to be more collisions. If there are more collisions, there are bound to be more effective collisions because some are going to hit right with the right amount of energy. But concentration isn't the only thing we can change. We can also change temperature. So remember the analogy when I said if we are both cooking eggs and I turn my burner up higher, my eggs are going to cook faster? Well, if we increase the temperature for a reaction, there's going to be more collisions. And also, those collisions are going to have more energy because remember, temperature is a measure of average kinetic energy. So particles at a low temperature are hitting like this because they have less kinetic energy. Particles at a high temperature are hitting like this. Okay, so those collisions have more energy. So there's two kind of pieces of it. First of all, there are more collisions. Second of all, there are collisions with more energy. Now, the more energy piece is probably more relevant, but both are increasing. On the flip side, if we decrease the temperature, there's going to be less collisions, and those collisions we do have are going to have less energy. So therefore, it's going to decrease rate. So far, if we increase concentration, we increase rate. If we increase temperature, we increase rate. Okay, so again, should you remember? When you increase the temperature, the particles are moving faster, so they're going to hit harder. And also, because they're moving around faster, they're just going to bump into each other more often. Temperature does affect some reactions in our daily lives. So we raise the temperature to speed up the chemical process of cooking. So I don't leave my eggs just on the counter and wait for them to be cooked. And we lower the temperature in the refrigerator and then the freezer to slow the chemical process of food spoiling. So we literally use it pretty much every day. Okay, so we had concentration, we had temperature, now we have surface area. What does that mean? Well, surface area is the number of particles on the surface that are exposed. Okay. If we increase the surface area, we have more collisions. So I'm going to show a visual on the next slide that may help. And this is going to increase rate because there's going to be more collisions. If, on the other hand, we decrease the surface area, we will have less collisions, and that will decrease our rate. So let's look at it visually. Okay, so let's look at it. So right here, you can see in this example is a big chunk, a big piece. Only those particles on the outside actually have any contact to be able to have a collision. If, on the other hand, we break it into small pieces and that increases the surface area, you can see how more of the particles are exposed to be able to have effective collisions. Okay, so how do we increase surface area? We break it into smaller pieces. Big chunk, only the outside pieces can react. All the pieces on the inside, they don't have any contact with the particles they need to collide with. So let's look at another visual. Okay, so here's an example. This is an Alka-Seltzer tablet and it's dissolving in water. So how could we make it happen faster? So we've talked about a few things. So do you have any ideas? How could we make this happen faster? All right, here's one idea. So look, here's the Alka-Seltzer tablet as it's in the package. Remember, if we increase the surface area, we could make the reaction happen faster. So if we break it in half, that's faster. What if we broke it into 4 pieces instead? Well, that's even faster. And what about if we crushed it, made it into a powder? Then it would happen even faster. So if you look at time, when you have big pieces, that's a low surface area, it takes longer. And if you have little pieces, the reaction happens faster. Well, what's another way? Well, we could heat up the temperature. So the Alka-Seltzer tablet would dissolve faster in warm water versus in cold water. So far, there's a few things that we could change. Now, you can't really change the concentration because we're dissolving it in water, so you can't really change the concentration of that, okay? All right, what about pressure? Well, you should remember from previous units that pressure really has an effect on gases. So if we increase the pressure, what are we doing? We're decreasing the volume, less space. If there's less space, guess what? There's going to be more collisions. So if we increase the pressure, we decrease the volume, there's more collisions. If there are more collisions, more are bound to be effective, which means the rate goes up. If we decrease the pressure, we increase the volume. that means there's less collisions and our rate is going to go down. So here you can see when you have low pressure, high volume, less collisions. If we increase the pressure, that means make a small volume, we get more collisions. Low pressure, less collisions. High pressure, more collisions. And then our last topic is a catalyst. So what is a catalyst? Well, a catalyst is something that speeds up the rate of a reaction. And if we add a catalyst, all it's going to do is lower the activation energy. That means, remember how we had to collide with enough energy? Well, all of a sudden the amount of energy goes down. It's like instead of building with these Legos, we're building with Duplos. Oh my God, way easier, okay? Less energy needed. Then that's going to increase the rate, okay? So if there's no catalyst, there's a higher activation energy, so the rate will go down. So a catalyst speeds up the rate. Now, if it's a reversible reaction, okay, it's going to speed up the forward and going to speed up the reverse, okay? So it's not really going to affect equilibrium, but catalysts absolutely do speed up reactions. They lower that activation energy, make it easier to go to completion. So which sample of hydrochloric acid reacts at the fastest rate with a 1 gram sample of iron filings? Okay, so here's what I'm going to do. You have two different temperatures. Which one is going to have a faster rate, higher temperature? So I'm going to get rid of the low temperature options. Okay, what else is different? Well, the 10 milliliters is the same. So I have this and this. What does that mean? Well, this capital M is molarity. That means concentration. And remember, high concentration speeds up the rate. So there's my answer. As the temperature of a reaction increases, it is expected that the reacting particles collide. Well, do they collide more often or less often as we increase the temperature? Well, they collide more often, so let's get rid of these options. And do they collide with greater force or less force? Remember, greater force. Which factors have the greatest effect on the rate of a chemical reaction? Okay, it doesn't even matter what substance at this point. Let's just look at the choices. So I have aqueous and I have a solid. So I know like pressure, no, pressure. Absolutely not. Pressure only affects what? Gases, right? So temperature, I know, yes, but then I can have solution concentration or molar mass. Which one? Solution concentration. Why can an increase in temperature lead to more effective collisions between reactant particles and an increase in the rate of a chemical reaction? Why? Because the number of molecules with sufficient energy, remember, as we increase temperature, we're increasing the average kinetic energy. Okay, so here's a reaction. Which set of reaction conditions produces H2 at the fastest rate? So again, at the end here, do you see I have temperature? What is the faster rate? Higher temperature. So I'm going to get rid of the 20 and get rid of the 20. I know I need the higher temperature. So now I have a lump, I have powdered, and I have 0.5 molar and 1 molar. So what reacts faster, a lump or a powder? Well, I know a powder reacts faster. And what reacts faster, 0.5 molar or 1 molar? 1 molar reacts faster. So it all worked together and came into that choice. And that is reaction rates. So I hope that you learned something new today.